All right, folks, let's go ahead and get started. So today's presentation comes from Dr. Sikai Chen, who's an assistant professor at the Department of Civil Environmental Engineering at the University of Wisconsin-Madison. He received his Ph.D. in civil engineering with a focus on computational science and engineering from Purdue University. Dr. Chen's research centers around three major themes: human users, AI, and transportation. He aims to innovate and develop safe, efficient, sustainable, and human-centered transportation systems using cutting-edge methods and technologies. The focus is on incorporating human behaviors, interactive autonomy, and intelligent control frameworks. He's a member of two ASCE national committees, Connected and Autonomous Vehicle Impacts and Economics and Finance, and TRB Standing Committee on Statistical Methods. Please join me in welcoming Professor Sikai Chen.
Thank you very much, Kevin. So good morning, ladies and gentlemen. So on behalf of the project team, Professor Sue An and Professor David Noyes, I will present to you about our mini-project update for our Sikai Year 1 project titled Using Connected Intelligent Transportation to Enhance Vulnerable Road User Safety. So this project started earlier this year in January, so we are about 4 months into the project, so there are still ongoing things, but what we will do is to go over some of the study background, why we are doing this, and what we achieved so far, and then what we plan to do moving ahead. So when we talk, the literature shows that the vulnerable road users suffered a lot from all kinds of traffic incidents. They account for about 46% of the traffic fatalities and about 53% of all the serious injuries. And this number has still going up in the past few years, even with the new technologies. So it's pretty a big issue. And when we talk about the VRUs, basically we refer to all the participants with most at risk in the traffic. So this include, for instance, bike riders, pedestrians, children, elderly, and visually or hearing impaired persons. So we try to look into the future because that's to try to align with the mission and also the vision of our Center for Connected and Automated Transportation. So we are thinking about not the traditional case, but in the era of the autonomous vehicle. Some of the traditional communication between the VRUs and vehicle may not be feasible. So if you imagine one very simple, like everyday scenario when we go across the street, if we see a vehicle coming towards us, right, what will affect our decision of keep going or like stop moving? We should probably consider like the speed and location, right? But then the literature also finds that the eye contact between the pedestrian and the driver is also an important factor. So for instance, if we know the driver also sees us, then typically we will be more confident about keep moving. Or on the contrary, even if the vehicle may drive super slowly, but then if the driver is look at the other side, not to us, right, then probably we will stop. But in the future, you are still gonna take a look at the driver's seat, but then it might be an autonomous vehicle, and then you may find nobody is sitting there. Then what we are going to do? So there's lots of challenge, but also the opportunities to try to use the emerging technologies such as the AI, the shared information, to build some system to capture this complicated interaction. And this type of interaction is also very rare to be found in the real world. So first, you don't see a lot of autonomous vehicle on the street right now due to the regulation issue and other challenge. And also, even if there's a autonomous vehicle, then interacting with a pedestrian may not be within a safety critical case. Maybe it's just a very normal interaction, and then that don't provide you any information. Or even if there's a safety critical case, maybe there's not a roadside unit, so you won't be able to collect that data. So that's basically motivate us to do this study. Try to gather information for all the researchers across the country or even across the world to try to develop some framework to capture this complicated interaction between the future autonomous vehicle and the vulnerable road users. There are three key technologies that we will explore in this research. First, virtual reality. as I just mentioned, there's data limitation, and in the real world, it's pretty difficult to collect such data describing this interaction. So we want to use virtual reality to try to provide an immersed setting for all the participants. And then through the VR, they are able to interact with the autonomous vehicle. And then we can specifically design all kinds of safety critical scenarios. The second thing is digital twin. So even though we try to come up with a framework that we can collect this data in the simulation, but we want to make the simulation as realistic as possible compared to the real world, including the road alignment, the friction, the weather condition, and so on, or the traffic signal. So using our lab-developed vehicle, we are able to drive the vehicle around with its LiDAR sensors to gather some information about the real-world infrastructure, so we can create a digital twin copy and combine that with the VR to provide such a realistic environment for our study. And the third technology that we will be exploring is V2X communication. Since we want to have, for example, maybe the VRU will be able to communicate with the smart roadside infrastructure, like through the cellular data, or talk to the vehicle, and the vehicle can also communicate with each other. Even though we will not study the hardware in this study, but in our simulation platform, we can try to simulate this shared information, including the information delay, package loss, and so on, to make our study more close to the real world scenario. We have been working for this project for the past few months. The major thing that we finished so far is to complete our study framework. So as you can see here, it's basically our task one. We call that virtual reality-based VRU and AV interaction framework. So in the middle, I'll try this clicker. Okay, so in the middle, you're gonna see our multi-agent human-in-the-loop simulation platform. So there could be, so let's say one participant acting as a truck driver, so driving this vehicle. There will be other participants wearing our VR headset and then try to interact with this connected vehicle or an autonomous vehicle with the driver sitting in there. We also want to pair that with some portable devices, such as the smartwatch, because if our AI determines there could be a dangerous case, then we hope to use those portable devices to send some warning message to maybe both the driver and also the pedestrian. And then with this simulation platform, we can further incorporate some traffic simulation capability. So within this digital twin, we can simulate all kinds of traffic scenario. We're going to talk about that in more detail in the later slides. But then our task 3 will be, after we have all this information, shared information, and then different scenarios, we try to design some VRU warning system. So when the dangerous case happen, maybe we'll send a vibration through the smartwatch. And then task 4 will be the AV VRU collision avoidance system. So maybe you may heard about those AEB system, automatic emergency braking. So if our system predict there could be a dangerous case, not only we want to send the warning message to the participant, but also our AI can maybe do some takeover to change the vehicle speed if the driver is sitting in an autonomous vehicle. So more detail about task number 2. Basically, you see this virtual reality interactive framework for us to collect the data. We will further do the integration of the Carla simulator with the Sumo simulator. So the role of the Carla simulator will be mainly about providing a 3-dimensional simulation space. And then another good thing about using Carla is there's lots of built-in sensors. So there could be LiDAR sensor, camera sensor. We can add all the sensors to any places. near the traffic light on the tall building and so on. And there are also a lot of vehicle dynamic model enabled in the Carla simulator. And with a Sumo integration, we can simulate, create this small traffic network with traffic signals. And then they also have many good built-in functions, such as a lane changing model or a car following model. So not only having a multi-agent simulation for all the participants, but we also want to simulate some of the background vehicle. And then with that, we will create our safety critical scenarios. So this shows 3 of the common safety critical scenarios for the vulnerable road user that we found in the literature. But along the study, we want to further design other scenarios, such as a big truck with a different like blind spot and so on. So our task 3 is to design the warning system for even though here we say it's for the VRU, but we actually also want to do this for maybe the truck driver and so on. So we're gonna start with the smartwatch, but later on we plan to also consider ways to incorporate the mobile phone. The reason we don't do the mobile phone in the beginning is that you imagine in our study the participant will be wearing a VR headset. Then that creates some challenge of if we send a message or send some screening to the phone, then our participant will not be able to check the physical phone since they are wearing a VR headset. But in the future, if we modify the framework to incorporate maybe the augmented reality glass, such as the ones developed by like Meta, then in that case, this incorporating the mobile phone will be more feasible. We want to leave this in the framework, but that's more about the future work. So there will be some measurement to try to evaluate if our proposed warning system is effective. So we are going to use some of the followings, such as a successful response rate, the response time, the misjudgment rate, or the successful collision avoidance rate. Our last task for this project will be try to design the VRU collision avoidance system for the autonomous vehicle. So using this figure as an example, so we can simulate different scenarios. Maybe a road segment with like a 360-degree camera on the top to provide a bird's eye view, or we can add maybe a LiDAR sensor to provide a point cloud like data. And then maybe our participant will try to go across this street, and then there will be a driver. We can distract the driver, but then our AI may do some predictions about their trajectory movement or collision risk. And with that, we can try to come up with some advanced decision-making algorithms. Those are AI-based or statistic-based. And then if we find something dangerous that may happen, then we can send a warning message maybe to the driver to take over. Or we can use some proactive control measures, such as when some value is above or below a certain threshold, the automatic emergency brake will be enabled, and then that will adjust the vehicle speed and so on. So basically, so far we have finished the study design, as we just talked about, and then there are also some preliminary work done. One of the key part is what I call the SkyDrive. Basically, it's a multi-agent, human-in-the-loop and hardware-in-the-loop traffic simulator that integrate Carla virtual reality WebSocket to provide the information sharing and communication protocol, and also ROS, because in the future we also want to incorporate some hardware, such as the real-world vehicle. It's a simulation platform developed by my lab at the University of Wisconsin-Madison. The main capabilities include simulate different vehicle dynamics and then use built-in sensor functions from the Carla. And then the key part, and that is also more related to this study, is this multiplayer. So there will be multiple client or computer or different equipment, and then all the simulation will be synchronized in a centralized server to study the interaction among different players with our complicated driving environment. So here is a general framework about the Sikai drive that we proposed so far. So starting from the part one, we basically mainly talk about the VR, but as I mentioned, in the future, we also try to integrate the augmented reality capability. But this really depends on what API that all those tech firms will be releasing, such as you probably heard about the Apple released their mixed reality headset, and then the Meta, I think a few years back they also start to sell their augmented reality glass. And this will allow researchers and developers to experience the simulation environment firsthand and enhancing the situational awareness. So, and this will also support of the human-machine interfaces and user interaction experiment design. So part two of the Sikai drive. So we talk about the Carla integration, basically try to provide more detail about the weather, lightning condition, road type, configuration, and so on. This will be our main test bed for this research. And Sumo integration, basically about traffic flow, traffic network, and with customizable scenarios, road layout, and then traffic signal configurations. Part three, multi-agent system integration. We already spent some time talking about this, but basically the key thing is to try to provide a synchronized environment for all the client, so they can all interact with a single simulation platform. So each agent will be able to operate with in the simulation as a discrete entity, and they all have their own power to perceive the environment, make their own decisions, share the data, or trying to mimic the real-world interactions. And later on, we also want to make this scaled up. So there will also be some coding issues we want to address to make this large scale. So hopefully in the future, we'll be able to deploy this on our centralized server, so the researchers from the entire country can use our simulation platform. So maybe you can wear a VR headset in your lab or in your room, and then trying to interact with the other participant in our simulation environment. It's like an online game, but for the research purpose. And then the fourth part is the hardware in the loop. We haven't done a lot of work so far, but teaming up with other researchers within the transportation group at the UW Madison, including Professor Xiaopeng Li. So we are trying to also incorporate some of the self-developed in-lab vehicles. So as you can see, we have this red one and also this black one from Professor Xiaopeng Li's lab. So these vehicles are capable of talking to the roadside infrastructure and then incorporate different sensor technologies. And then we want to have our simulation platform also twinning with the physical world. So you can imagine a case that in the future, our lab vehicle is doing its test in a controlled environment with no participant or no surrounding vehicle, so it's totally safe. But then our researchers are wearing a VR headset and staying in the lab and then trying to interact with a real-world vehicle, but in the simulation environment. So in that case, so let's say the AI may fail or some hardware in the vehicle may fail, but our participant will be still safe. So here is basically about our multi-client communication structure. So as we mentioned, we hope to have multiple computers to connect it to the same simulation platform. They may not just be computers; they can also be hardware, like the vehicle that we just showed. So for now, we have a simple case. We have a centralized server in the middle I apologize for the small text, but then our centralized server will be basically simulating the entire Carla and Sumo environment. And then we have 2 clients in this case, connecting to the centralized server. Maybe they can be the VR equipment, or they can be some other normal computer with the driving simulator installed. So through this structure, we hope to provide a real-time interaction, and then we want to scale it up and also provide the cross-platform capability. So far, there are still some challenges that we need to address. For instance, if we have more than, let's say, 4 or 5 agents connected to a centralized server, and then if our synchronization frequency is very high, then sometimes you may see weird cases. Maybe the vehicle on the individual computer are teleporting in some cases. So we are still trying to optimize our code to make the framework more reliable. So here, I want to briefly mention, even though this is not directly related to this Sikai Year 1 project, but at the University of Wisconsin-Madison, we actually have a larger digital twin initiative working with all the colleagues in the transportation group. So basically, we are trying to create a digital twin copy. So using Professor Lee's vehicle, we are able to drive the vehicle for a couple of times, for example, on the flex lane in Wisconsin-Madison. And then with LiDAR, we can create those point cloud data as shown here. It's overlapped by another picture, sorry. Yeah, but with this point cloud data, we will be able to reconstruct the real-world road alignment in our simulation or digital twin platform. And another thing we did is that you see that there are some cameras along this like belt line or flex lane. And then we are able to access the real-time traffic video surveillance data. And then using the computer vision, we can then extract all the vehicle trajectory. And then when we have the vehicle trajectory, we can re-simulate them back in the simulation. So not only we have a digital twin copy about the road infrastructure, we are also going to have the digital twin copy of the movement of each of the vehicle. So with this platform, we can further enable multiple functions in the future. For example, we can do the real-time traffic monitoring or traffic management. If there's an emergency happen or like a collision happen, our AI can automatically detect the crash location. And then since we have all the trajectory in the past, we can maybe simulate back about like 1 minute or even 2 minutes. So we can show to the traffic operators about what lead to that crash. And then since all this will be in the simulation, like a real-world copy, then we can also try to simulate different ways or different strategies to do the maybe the lane closure and then also evaluate their impacts. And we can also try to predict maybe the high collision risk location and so on. So even though this work is not part of this study, but I want to mention the SkyDrive that were funded by the Sikai Year 1 research can actually make a more broader impact to the society and then to the real city. Some other preliminary work so far. So for example, we start to think about the truck blind spot accident. So the literature shows that annually there are over 520,000 truck accident annually across the country. And many of those are caused by these extensive blind spots. So from this figure, you see that we had not only have the blind spot on the 2 sides on the back, but it's also in front. So to me, I found the video here. So such risk or such collision in the first place are not really even make sense to me. But since I think especially for many people who are not an expert in the traffic safety, right? So you can imagine there could be blind spot on the back, but not in front. But these things actually happen in the real world. So trying to show a demonstration of our proposed Sikai drive. So here is a multi-agent scenario. We have one of our grad students driving a small truck, and then another participant wearing a VR headset, and then trying to act as the pedestrian in this intersection. I apologize that this video may not synchronize really well. But the point I want to show you is that at this time step, you see the pedestrian is off the view of the driver, right? So that's is one scenario that we are trying to design to show about the blind spot of the truck driver case. So later on, we hope all the researchers can use our platform to create scenario like this, and then some of the vehicle could be a maybe level 3 like automated truck, and in such case there should be a warning message designed and also provided to the driver or also to the pedestrian. So you are in the blind spot of that truck. So that is what we have done so far, and moving forward, there are a few things that we plan to do. First, study this interaction among the VRU and then the all different kinds of vehicles are very complicated. We don't believe that just using the trajectory information is enough. So one thing that we are thinking is to use this biomechanical movement. So you see those like little straight lines trying to capture the body movement of the VRU. So we want to further incorporate this into our simulation platform. So we can build some AI system to try to better analyze the VRU's intention and build some motion prediction model for the pedestrian. And teaming up with many other colleagues at the Madison, we are also trying to develop more advanced AI to also predict the vehicle behavior. So in this case, we are trying to integrate the physical model and the learning-based model to come up with a new predictive AI, what we call the Pearl. So the high-level idea is that when we have the data collected, and then we don't just use one single model to close the gap between the data and then the true state, but instead we try to use existing physical model that has a higher interpretable power to maybe explain about 70% of the entire variance, and then use another learning-based model to close the remaining gap. And that is this residual learning part. So we can try to close the distance between our data and then the true predictive state to have a better prediction of the vehicle behavior. I'm going to skip the detail here, but the main idea is that we also want to evaluate how much data we need for such physics and also AI integration. So maybe when we have only limited data, we find one way is working better than the other way. But if we have a huge amount of data, maybe we should try to combine the physics and AI in a different way. We are also working on trying to improve the more functions into the Sikai drive. For example, the eye tracking capability. So we found in the literature that the eye tracker can make the driver more awake and also more alerted, so to provide a better situational awareness. And also, since we are in the state of Wisconsin, so previously most of the so far what we designed is for the normal weather condition, but in the future we also try to have our simulation platform to be capable of simulating like snow and rain. And a little bit more far away from the future is we also want to try to deploy this to do some pilot test and also demonstration in the real world with the lab vehicle that we have. we have already started to do some very preliminary work, but after the SkyDrive is finally built and we have a better integration of the hardware with our simulation platform, we want to take into account this perception delay, perception error, and so on. And we have already initiated some of the collaboration with our local partners for the test case. So here we have the Madison College Public Safety Training Center. Basically, as far as I know, they use this center to basically train the state patrol. So when they need to pull over some very aggressive driver, but over the weekend, we can try to use their testing track since they have multiple lanes, and then we can do pretty aggressive maneuver there. So here is a reference list, basic about all the information that support this study. And I want to thank our research sponsor, Center for Connected and Automated Transportation, led by the University of Michigan, and our center director, Professor Henry Liu. And without their support, there's no way that we can do this research. And also, I would like to acknowledge the great researcher and also the student in my lab. And all the work you saw are teamwork. And without their dedication, there's no way that we can come to this far. And even though not all the students are funded by this study, but they all contributed to this research in one way or the other. Yeah, so thank you very much for your attention. I would like to take any comments or questions that you may have.
Any questions in the room? Yeah.
Which form of feedback to the vulnerable road user did you find was the best one? Was it haptic? Was it audible? I'm interested in the findings of actually how people interacted with the devices.
Right. So in the proposal, we mentioned that is one of the major things we want to study. But since we are only about like 4 months into the project, so we want to test all the things you mentioned. So we will definitely mention that in the final report. Yeah. But so far, from the other study and that we saw in the literature, the vibration seems to work better than the audio one, since people may wear their they may listen to the video like while they're working, so they may pay more attention to the vibration. Yeah.
So I know you talked about signal infrastructure in one of your slides. So I was just wondering what the interaction, what do you consider during interaction, like signal infrastructure at an intersection, say the pedestrian or any kind of vulnerable road user, like signal infrastructures at an intersection and a vehicle at an intersection. So did you guys consider such scenarios in your study, and if maybe the information is it passing it down to the vehicle or to the signal infrastructure or whatever infrastructure, even at mid blocks too, if you have an infrastructure there?
Right. So basically, we are considering to incorporate those traffic signals. So was that your question? All right. Yeah. So basically, from the even though we don't have some like statistic evidence to show here, but intuitively we think the safety critical case may actually happen when there's a traffic signal, since in our daily life, we observe that for many like pedestrians, for example, when they see the light turns to green, so they start to walk, and sometimes they walk with their phone in their hand. But then this could be specifically dangerous if there's a aggressive driver trying to run the light, right? Then that's actually more dangerous than the case without the traffic signal. So that will be something that we will definitely consider. And then in many signalized intersections, there are like surveillance camera. So we are also trying to team up with the city of Madison to use their real-time surveillance video like data, so we can track the VRU's movement and then the vehicle movement. And then if we find some sign that one vehicle may run the light, then that should be the time that we send a warning message to the pedestrian.
I have a question about the people's behavior. If you look at people when they're crossing, there's three things that they do. Typically that they stop, or they can go back, or they can go forward. Have you been looking at how you are going to be modeling the behavior of a person in the digital twin? I'm curious about how, because some people react differently. Some of them will follow others, some of them will freeze and stop, and some of them will go back. And how did you find out about the behavior from the person, and then what would be the connected vehicle or the autonomous vehicle will do for something like this?
Yeah, I think that's a very good point. And sorry, I don't have an answer for now, since we are only finishing trying to develop our simulation platform. But I will keep that in mind and then trying to capture, I guess that's pretty personalized. And that's why it's important to have a framework like this, so we can all design our own scenarios.
Other questions in the room? Okay, well, please join me in thanking Professor Chen. So we've ended this session about 25 minutes early, so I highly recommend you go next door for our advanced air mobility panel. And then at 12:15, we'll break for lunch.